Okay, this is problem number 1. It says find the amplitude, period, and phase shift of y equals -3/4 cosine of pi x minus 2. The amplitude is just a in that equation, so a is 3/4. So our amplitude is 3/4. The period is 2 pi divided by b. So we have 2 pi. Our b in this equation is in front of the x, so we have pi. So that's just 2. So the period is 2, and the phase shift is c over b. And our c is 2 divided by our b, which is pi. So our phase shift is 2 pi. And it's positive because what's inside the cosine is pi x minus 2. So we know that phase shift moves to the right, so it's going to be positive. Okay, this is problem number 2. It says if alpha and beta are acute angles such that the cosecant alpha equals 13 over 12 and cotangent beta equals 4/3, find the sine of alpha plus beta, the cosine of alpha plus beta, and the quadrant containing alpha plus beta. So I have the two triangles. On the left is the triangle for angle alpha, and I've already labeled the sides 5, 12, 13. And the second one is angle beta, and using that they gave us the cotangent of beta is 4/3, I found the sine of beta and the cosine of beta. So now all we need to do is we need to know, the first question is find the sine of alpha plus beta. That's one of your formulas, so it's sine of alpha cosine beta plus cosine alpha, sine of beta. All we need to do is plug in, so we know sine of alpha is 12 over 13, sorry. Cosine of beta is 4/5, plus cosine of alpha is 5/13, and sine of beta is 3/5. So let's simplify. We know that these 5's will cancel, and when you multiply across and add the fractions, you get 63 over 65. 63 over 65 is a positive number, and since this is sine of alpha plus beta and it's positive, we know it's either in quadrant 1 or 2. So I'll write quadrant 1 or 2 off to the side. Okay, now we need to find cosine of alpha plus beta, and that equals cosine of alpha, cosine of beta, plus, minus sine of alpha, sine of beta. So plugging in our numbers again, cosine of alpha is 5/13 times cosine of beta is 4/5 minus sine of alpha is 12/13 times sine of beta, which is 3/5. Again, simplifying, we can cross out the 5's here. So we have 4/13 minus these two fractions multiplied together, and that will equal negative 16 divided by 65. And cosine, this is a negative, so when is cosine negative? It's either in quadrant 2 or quadrant 3. And the last part of this question says the quadrant containing alpha plus beta. So alpha plus beta is in quadrant 2. Since both of these have sine of those is either in quadrant 1 or 2, and then cosine of those is either in quadrant 2 or 3. So when you add alpha plus beta, it has to be in quadrant 2. Okay, this is problem number 3. It says when the top of the Eiffel Tower is viewed by an observer at a distance of 250 feet from the base, the angle of elevation is 60 degrees. Draw a picture of the situation and determine the height of the tower. Okay, well, I've started with the picture. I'm going to draw a little person next to my angle. And says the observer is at 250 away from the base of the base of the building. So if I draw my building here, the top of the Eiffel Tower is viewed by an observer at a distance of 250 feet from the base, and the angle of elevation is 60. So when the observer looks to the top of the building, that's 60 degrees, and that's indicated where I have it on the triangle. So we drew the picture, and now we need to determine the height of the tower. So we need to solve for h. So we have an angle, and we know that the tangent of 60 equals opposite over adjacent. So we have h divided by 250. We can cross multiply to solve for h. H equals 250 times the tangent of 60 degrees. And that equals 250 times sine of 60 degrees divided by cosine of 60 degrees. And we know the sine of 60 degrees is the square root of 3 over 2. Cosine 60 is 1/2, so we're going to times it by 2 over 1. So we get 250. These 2's will cancel, so times square root of 3. So that is our height.
Alright, so for the upcoming problems, we are asked to graph these different trig functions. So we have written the general formulas for our sine function underneath this problem in the a and b's and c's, the general format. So let's get down what we know just from looking at that. We know that the amplitude is our a value, so that's going to be 3/2. We also know that we have a vertical shift, which is our d value, and that vertical shift is -1/2. So next up, we know for our sine function, a general one has a period of 2 pi, so it's bounded from 0 to 2 pi. Now this just represents a general sine function, a sine of x. We have a sine of x minus pi over 2, so we have to take into account for the phase shift in that. So we can write that as 0 is less than or equal to x minus pi over 2 is less than or equal to 2 pi. By plugging in the inner workings of our sine of x minus pi over 2 into the normal bounds of 0 to 2 pi, we can then solve for the x value to incorporate our phase shift into our period. So what we're going to do, we need to solve for x. So we'll add a pi over 2 to every side. That cancels out the pi over 2 in the middle, and in addition we're going to have pi over 2 on the left side. So pi over 2 is less than or equal to x, and then pi over 2 plus 2 pi, that will give us 5 pi over 2 on the right. So now that we have this bound represents one period of 2 pi for the sine function, the sine of x minus pi over 2. All that happened here, our period did not get adjusted, it just got shifted over to the right by a factor of pi over 2. Alright, so now that we have one bound of one period from pi over 2 to 5 pi over 2, let's get to graphing. We've talked about up top that the vertical shift is -1/2. So let's kind of pretend to move our x-axis down to y equals -1/2. So we drew a black line in here. Now we'll get to graphing. We see that given by our bounds, our first point of our sine function is going to be at pi over 2, and that's going to be at the y equals 1/2 part. And we know, finally, just by looking at a sine function, we know it's going to end and 2 pi more, so at 5 pi over 2, given by our bounds, also at 1/2. And then also, once again, same theory, we know that halfway through a sine function, since it looks like a sideways S, it's going to cross our imaginary x-axis at y equals -2 again. So, given the fact that we know our amplitude now is 3/2 instead of just 1, we're going to have to take of that for our remaining 2 points. And since our sine function is kind of a sideways s, we know that at pi, that's going to be our maximum point. But since we have a amplitude change of 3/2, this is going to end up being at 1. So we found our maximum point, and that's at pi. And so our minimum point is going to be at 2 pi, and we have to count for the 3 over 2, amplitude. So at 2 pi, our next dot will be at -2. So now we have all our points, our necessary points, to graph this, and we just trace our sine function, and we are done. So for this next equation, the y equals negative cotangent of x plus 1. Let's get started. First off, we've discussed in class that cotangent has a period of just pi, not 2 pi. So for the bounds of this one, since we have nothing to deal with on the inside of the cotangent function, it's just x, let's make our bounds from 0 to pi. So at 0, along the y-axis, we're going to have asymptotes. And then since we're going to pi, we'll have an asymptote running at x equals pi also. Now, we also have a vertical shift of plus 1 on this. So midway between our bounds of 0 and pi, we place a point at pi over 2, 1 on our graph. So we're almost completed now, and we see that we have a cotangent function, but since we have that negative sign in front of the cotangent function, it's essentially just going to make a tangent graph. And a tangent graph looks something like this. And there we go. Nice and simple. We're done. For our final graphing equation, we have y equals 1/2 secant of 2x. So let's start with stuff that we know right away just from looking at the equation. The only thing here we have is we know our amplitude is going to be 1/2. So secant is the inverse of cosine function, and a cosine has a period of 2 pi. So when thinking of it, we can think of this as a cosine function from 0 to 2 pi, and we can bound it by that. And using the same strategy that we have for the previous problems, we have to account for the 2x, which is within the secant. So let's bound that 0 is less than or equal to 2x, which is less than or equal to 2 pi. Now, to account for our period manipulation, we just need to solve for x in this. So we've divided through by 2. We have 0 is less than or equal to x, which is less than or equal to pi. So 1 period of our secant or cosine function, however you want to think of it, is going to go from 0 to pi. So like I mentioned before, we can view this as a cosine function, so we can just get a general sketch of what this might look like. So given our amplitude is 1/2, we've drawn in little dashes between 0 and 1s, and we can consider those 1/2. So with cosine function, we're going to start at 0, and our amplitude, as we've talked about, is 1/2. So we'll place a dot at the 1/2 on the y-axis. And then we know a cosine finishes at pi given by our bound, so we'll also place another dot at 1/2. And another thing we know about the cosine function is that halfway through, we're going to hit our minimum. So our minimum with our amplitude is going to be -1/2. So let's place a point there. And then the rest of the cosine function, we know that halfway in between 0 and pi over 2, we are going to be crossing our x-axis. And we know the same thing between pi over 2 and pi, that we'll be crossing our x-axis. So now we can sketch out a basic cosine function. Alright, since we have graphed our cosine function, we can now start thinking of this function as a secant function. First, with secant functions, we need to think about the asymptotes. And the asymptotes occur when our cosine function crosses the x-axis. So I'll draw in these dotted lines as our asymptotes. So with these asymptotes, they represent where a function doesn't exist. They get infinitely close, but does not exist. So the remaining part of this, we know that secant is just our cowbell-looking shape, if you will. So at the dots running along the asymptotes, we're going to draw on our cowbells. So in the middle, we're going to have a full upside-down one, and on the sides, we're going to have little half ones that run up our asymptotes. So the green color indicates our final graph of our secant, and the black is just a cosine sketch that we did. Alright, for our next problem, we're asked to verify the following identity of secant squared x minus 1 times cotangent of x all over the tangent of x times sine of x plus cosine of x, and we got to prove that equals sine of x. So for our first step, let's look at the top part of the left side. We see we have a secant squared x minus 1. We can rewrite that as tangent squared of x. So on the top, we'll have tangent squared of x times cotangent of x all over the remaining tangent times sine plus cosine. Next step, we could simplify the top a little bit. If we look at the top, we see we can rewrite tangent squared of x as tangent times tangent. So when we look at tangent times cotangent, they are inverses of each other. Being inverses of each other, they will essentially undo each other and cancel each other out. So I'm just going to write up here tangent as sine over cosine, and then cotangent is cosine over sine. So we can see that those two will cancel each out to give us 1. So on the top, we can simplify that down to just plain old tangent. So remaining, we have tangent x all over tangent x sine of x plus cosine of x. The remaining step, we can try to simplify down, and let's multiply both the top and the bottom by a cosine of x. In doing so, we simplify it down to sine of x all over sine squared of x plus cosine squared of x. And the only step we have remaining, as we see on the bottom, we have our Pythagorean identity of sine squared of x plus cosine squared of x. That is equal to 1. So remaining, we have sine of x over 1, which is simply sine of x.
Okay, this is problem number B. We have to verify that cosine of 3 theta equals 4 cosine cubed of theta minus 3 cosine theta. And with this one, we're going to work with the left side because we can break up cosine 3 theta into cosine 2 theta plus theta, and then use the sum identity, and that's cosine 2 theta minus sine 2 theta sine theta. And now we can go ahead and rewrite that. We're going to use the double angle formula for cosine 2 theta, and that's just 2 cosine squared theta minus 1 times our cosine theta, which is left, minus our double angle identity for sine 2 theta, which is 2 sine theta cosine theta. And then we still have our sine theta. And let's distribute the cosine through and sine through. So we have 2 cosine cubed theta minus cosine theta minus 2 sine squared theta cosine theta. Okay, now we're going to rewrite sine squared with cosine, because with our answer we needed to get to 4 cosine cubed theta minus 3 cosine theta. So we still have 2 cosine cubed theta minus cosine theta. minus 2 times 1 minus cosine squared theta times cosine theta. And now again we're going to distribute the cosine theta in. So we still have 2 cosine cubed theta minus cosine theta minus 2 cosine theta plus cosine cubed theta. And now we're just going to group together like terms. So we have, I'm sorry, this should be a 2 cosine cubed. We have 4 cosine cubed theta minus 3 cosine theta, which is what we needed to verify. Okay, this is problem number C. It's verifying cosine t divided by 1 plus sine t equals secant t minus tangent t. So what we're going to do is we're going to work with the left side, and we're going to times the cosine t over 1 plus sine t by the conjugate. So we have cosine t divided by 1 plus sine t times it by the conjugate, so it's 1 minus sine t divided by 1 minus sine t. Okay, and now we can distribute and get cosine t times 1 minus sine t in the numerator. In the denominator, when we FOIL that, we get 1 minus sine squared t. And we can write the 1 minus sine squared t as cosine squared t, so we still have cosine t times 1 minus sine t in the top divided by cosine squared t in the bottom. And we can cancel cosine out in the numerator and the denominator, so we have 1 minus sine t in the top divided by cosine t. And we can split that up into 2 fractions, so we have 1 over cosine t minus sine t over cosine t, and that equals secant t minus tangent t.
For our next problem, we're asked to find all the solutions on the given interval to negative 2 pi to 2 pi of the given equation. So looking at the equation, we see that we have a sine of 2x. So we could use a double angle identity to get rid of that 2x and rewrite this equation. So let's do that. So we're going to end up with 2 cosine x minus, and then the double angle identity for sine of 2x is 2 sine of x times cosine of x, all equal to 0. So now we want to get common factors pulled out and together so we can somehow find a solution. So looks like we have a cosine on each part, so let's factor out a cosine, or perhaps a 2 cosine even. So doing that, we factor that out, we'll have 1 minus sine of x, all equal to 0. So now we have 2 terms. We can take each of these and set them equal to 0. So we're going to have 2 cosine of x equal to 0, and 1 minus sine of x equal to 0. So with that, we now need to solve for sine and cosine. So it'll be just cosine of x equals 0, and then on the other side it'll be sine of x equals 1. Now, we need to find all the solutions for cosine when it equals 0. So we know that looking at our unit circle, at pi over 2, cosine is 0. At 3 pi over 2, cosine is 0. So we can write those ones down. And we have to take a look at the interval here. We're not going from 0 to 2 pi like we typically do. We're going from negative 2 pi to 2 pi. So we're going to have to go around our unit circle backwards also to get all the solutions for cosine. So if we're going backwards, we're going to go around negative pi over 2, which would be equivalent to 3 pi over 2. But we're going to write it as a negative. And then we're going to keep on going, and we're eventually going to hit negative 3 pi over 2, which on a normal unit circle would be looking in between the first and second quadrant on the y-axis. So that's our cosines right there, kind of separate that. So in the interval from negative 2 pi to 2 pi, we have 4 occasions where cosine can equal 0. So let's go over and take a look at our sine of x equals 1 and find out where that works on this interval. So we know sine of x equals 1 when we're in the first, we're along the y-axis on a unit circle in between the first and second quadrants at pi over 2. We're going to keep going around a unit circle. We hit 3 pi over 2, but that's going to give us a negative 1, so that's not an answer. So it looks like we've covered the positive 0 to 2 pi, so let's go and find the values for sine of x equals 1 from 0 to negative 2 pi. So if we're going the opposite way around the unit circle, we're going to have to go a negative 3 pi over 2 to get back up in between the first and second quadrants to give us a positive value of 1 for sine of x. So in this given interval, we found 4 different occasions where cosine of x equals 0, and then we found 2 occasions where sine of x equals 0. So we can just kind of combine these terms and condense them to write down our answer. We'll just have plus or minus 3 pi over 2, and also plus or minus pi over 2.